So we've discussed the flow of these instructions and the pipeline diagram of this out of order machine up till cycle 8. So at this point, you can maybe pause and then try out the rest of the cycles on your own and compare if it is correct as compared to what I'm going to now describe. So I'm going to describe cycle 9 onwards. So cycle 9, we do not have what is called the reorder buffer. So we have assumed there is no reorder buffer, and therefore the write back can happen out of order, which means that multiple instructions can write back in the same cycle, assuming that there are multiple register write ports so that you can do write back parallelly. We also assume that future instructions can write back before the previous instructions have written back. So instruction 3 is able to write back, although instruction 2 has not written back. So these are our assumptions, and that is why we do not have a reorder buffer. So later on, we will run through the same similar example and see what happens with the reorder buffer. So right now we can do the write back of instruction 3 before instruction 2 has written back. So now in this cycle, the fourth add is going to write back, which means that it is actually broadcasted the result onto the CDB, and then the CDB is actually writing the result onto the uh, reservation station and to the RAT. So which means that R10 gets its value. This was the one which was containing the value, the tag C. If we go back to the previous slide, this contained the tag C. So now this is going to get the updated value. And similarly, the this reservation station was dependent on C. So now that is also updated with the value so that it can go ahead and get issued in the next cycle. So now these are the updates in cycle 9. So if we move to cycle 10, you continue with the execution of the add instruction, and the multiply has been now issued to the functional unit. Then if you go to the cycle number 11, the add has completed its execution, and the multiply is continuing its execution. The last add instruction is dependent on the mul instruction, and therefore that has not yet started its execution. And this add instruction, you can see it here. This is the R5 which has been updated with or renamed with D, and this is the reservation station. So it is waiting on this reservation station to uh, on that functional unit to provide the value. So nothing else is happening in cycle 11. If we move to cycle 12, the add is going to broadcast its value onto the CDB, to the RS and the RAT. So you should now check which are the contents that are going to get updated. So if we go back to the previous slide here, R5 has been renamed to D. So if we now move to the next slide, so these are going to get updated now. So at this point, it is important to note that the second add instruction has the destination R5, whereas the last add also has a destination R5. Now remember that the first add, that is the second instruction add, was actually in this reservation station renamed to A. That was the first rename tag. And now that is being now broadcast. But actually this has now been already renamed to D. So A doesn't exist here. So this D is not going to get updated here. That is why we're not updating this value. Only those tags which have A as the tag are going to get updated, and that the only place where A is being used is this particular instruction. And that is this instruction here, the source which has been renamed to A. So that is important to note. We are not updating the register allocation table because this does not have the tag A. So A equals 6 is now broadcast, and it's going to now update only this particular reservation station. So I'm updating this reservation station to its value, and then we have freed up the A reservation station. Now this D, so if you see D, the destination is R5, which means this particular instruction is still waiting because the previous one is yet to complete. That is, this mul is yet to complete. So that is continuing to execute. So if we now just fast forward, I'm not showing 13, 14, and 15. So we assume that by cycle number 14, the multiply has completed and it has broadcast the value. And in 15, it is writing back, which means that f equals 136 is going to get written onto the RS and the RAT in this particular cycle, which means now the last instruction, which is yet to start its execution, is now going to get updated. So the RAT has now the updated value, and then the value has also come into the reservation station. Now, what happens is the last add is going to start its execution, and I'm not showing it here. And then it starts its execution in cycle 16, 16, 17, 18, it's going to complete. And then in 19, it is going to broadcast and update the RAT. So D equals 142 is the last one. Note that we have freed up all the other reservation stations. The only one that is yet to complete its execution is the last add. That is why we still have this destination renamed to D. So now that has also updated the RAT in the next in this cycle, and therefore we are now freeing up all the reservation stations. So this is now the final content of the RAT, and then the RS is now freed. So now another important point that I would like to make here is, let us look at another example, a simple example which has three instructions. Now the question I want to ask is, now R3 is the first destination which is going to be renamed. So let us assume that it has been issued to this reservation station and therefore it is first renamed to E. And similarly, the ad gets issued to the first reservation station and its name is A. So R5 is the destination which gets renamed to A. So let me repeat, the first multiply is going to get issued to the reservation station E, and it has been renamed to E in the RAT. The second instruction add, whose destination is R5, has been renamed to A because add has been issued to the reservation station A. Now, of course, you can also update the sources here, but that's not the key point. The point is, now the third instruction add comes in. It also has the destination R3. Now it is going to get issued here to the second reservation station for add, which is B, and its destination R3 is going to be now renamed to B. So although I'm showing E and B here, what actually exists is only B, which means the latest name for R3 is B. Now, what we have not shown in this Tomasulo machine throughout this exercise is we have not shown the content of the main physical actually the architectural registers. The correct name is architectural registers. We have not shown the content of architectural registers. We have only shown their content in the RAT. But there's actually R1, R2, R3, etc. up to R11. These are the architectural registers which finally get updated, and that is not something we have shown in this exercise. Okay, so let us now see the question here. Now, during the write back, we always said that the CDB is going to write to the RAT and to the RS, but it's also going to write to the architectural registers. That is the FP registers. If you see the Tomasulo machine, there was what is called FP registers, floating point registers, to which the CDB is going to write back. Now, the question I have is, let us say the first R3, which is the E value, right? The E value, that is the multiplication instruction, completes its execution and writes out the product, E equals 10, let us assume. Now, during the write back, during the register update phase of the write back, how does the register R3 get updated? Now, I want to update finally R3 to 10. Now the only connection between R3 and the tag E existed in the RAT. And this is the only way I can recognize that, okay, E equals 10 means R3 equals 10. Now since I have again renamed it to B, it means that I have lost this connection between R3 and E. So now how am I going to recognize and write back to R3 in this design? How am I actually going to write back to register R3? Because there's no way I can find out that E means R3. So that is a question. During the register update, how does the execution unit or the CDB know that it has to write back the value of E to the register R3? Now, you can think about it before I move on to the next slide. Now, this is what is called as the Tomasulo without the ROP. And in this case, the way you do it is as follows. Now, we know that the rename registers the registers have been renamed to the reservation station names, as you see here. And we are also not freeing up the reservation station. Now, there are two ways to write back the content of R3 by recognizing the connection between E and R3. Now, the first approach is, why do you need to update R3? Do you actually need to update R3? Is this value of R3 being used in any other instruction? Now, of course, this add is going to use this R3, but it is not actually reading it from this register R3. It is actually reading it from the CDB directly. And that is still possible because if you look at this particular this particular reservation station here, if I go to the previous slide, this reservation station still carries the tag E. So when the CDB writes the content E equals 10 or E equals 20, whatever, so it is going to recognize a tag and take the content of this E here and continue with its execution. So you do not actually need to read from register R3. That's the first point. So any dependent instruction does not need to read the content from the architectural register R3. So one of the approaches is you do not need to update the register file at all because you do not have a connection between E and R3 in the RAT. That's the first approach. Of course, there will be exceptions, and if there are exceptions, how do you handle it is a different question. Now, I have not covered exceptions here, but uh, I can briefly tell that exceptions happen either through hardware or software, and they are, for example, you can consider them as errors or as interrupts. Actually, you can consider them as interrupts, and when interrupts occur, you will need to note the value of the architectural registers. Now, if you do not update the architectural registers, how do you handle exceptions? So that will have to be handled differently. You may have to roll back the state of the processor to a different state and so on. Let me not go through that right now. So one of the approaches to answer our question is you do not update R3 because you do not see a connection between E and R3. That's the first approach. The second approach is you can add what is called a destination field in the reservation station. This is going to carry that tag, tag of the original register. So E reservation station is going to tell that the destination is R3. So now here you can establish the connection between E and R3, and therefore you can write back to R3, the architectural register R3. So this way, it is important that you do not release the reservation station or you do not free up the reservation station until you complete the register write back. So these are the two approaches in which you can handle this particular question.